Hello everyone. Okay, in this session we are going to study hydrostatic forces itself, but this is part 2, slightly more than whatever we have discussed in the last class. Of course, I'm going to revise many things of the earlier session, and then afterwards we'll go for further details. These definitions already you know. Pressure intensity is nothing but force per unit area. We have discussed in length this one, and units are Newton per meter square. Total pressure is nothing but total force acting on whole area. That will be nothing but pressure intensity multiplied by area. Units will be newtons. Center of pressure is nothing but the point where the resultant force is acting. The point of application of that force is known as center of pressure, or as just Cp. Now the submerged surfaces can be horizontal, vertical and inclined. We have already done horizontal and vertical parts. Inclined we are going to see today in detail. Okay, hydrostatic forces on plane horizontal surface. You know that intensity of pressure at any point P is equal to gamma into H, where gamma is the unit weight of the liquid. Okay, yeah, gamma is the unit weight of the liquid, and H is the depth. Now in this case the depth is uniform, means if the plane is horizontal, the depth will be same everywhere or every part of the surface. Because of that, whether you call it as H or H bar is nothing but depth of center of gravity. So that will be the pressure intensity multiplied by area will be giving you the total force. The notation it has been put as P, but we generally use capital F also. So general expression for force, total force, or means total pressure, which is referred to as total pressure, is given by gamma A H bar or gamma A Y bar. Right? Gamma is the unit weight of the liquid, A is the area, H bar is the depth of center of gravity or depth of centroid from the free surface. Okay, I talked about Varignon's theorem last time. Just to revise the same thing, here I got an object ABC. The length AB is 3 meter, B to C is 1 meter. There is a force 20 kilonewtons here at B, and then 30 kilonewtons at B. Now if I want to replace these two forces and place it on ABC, so that it will have the same effect. Now here the theorem to be used is sum of moments of these forces should be equal to moment of the resultant. That is what the concept we use. So if I take moment about A, for example, you can take moment about any point A, B, C, or anyone that you can choose randomly. But here for convenience I have chosen point A as the reference, and moment caused by 20 kilonewton is equal to 20 into 3, and it is clockwise. I have taken clockwise as positive. Then the force 30 multiplied by this whole distance 4 meters, 30 into 4. So that will be giving you sum of moments of the forces is equal to moment of resultant about the same point. We don't know where exactly this distance is, but resultant force, because it is all vertical force, resultant force will be equal to 20 plus 30. That will be 50 kilonewtons, which will be known. So R into X, general expression, but R is equal to 50. Because of that, I can find out the X, which will be equal to 3.6. So if we look at this figure, 3 and 1 more meter, so somewhere there the resultant force will be acting. When you remove them, you have to place a single resultant force. So definition of the resultant itself is nothing but single replacing force. So how to find out position of the resultant? Using Marignon's theorem, which states that it is sum of moments of all the forces is equal to moment of the resultant. That's what it is. Okay. There is one more concept of moment of area. Now moment of a force is a force into distance. Moment of area is area into distance. Now there is a reference axis AB. Reference axis AB. You got some random figure. We have considered only a small elemental area dA, which is at a distance y. Now what is the moment of this elemental area about AB, which will be nothing but dA into y, or y dA. Now if I want moment of all this area about AB, I have to integrate. So integration y dA, and this will be equal to A into y bar. What is y bar? Y bar is depth of or distance of centroid or center of gravity. What is A? Capital A is nothing but this total area. So if you want moment of area, you should just multiply the total area multiplied by its centroidal distance. That's what it is. We have used it in the proof. That's why I am revising. Okay, next is okay, here I have discussed moment of inertia. For plane figures, if there is no mass in existence, it is called just second moment of area. Otherwise it is called as mass moment of area. So in this case it is only area, that's why it is second moment of area. Now you have seen that the dA multiplied with y, we called it as moment of area. If you multiply once again by y, obviously we should call it as second moment of area, and y squared dA would be the moment of this small area about an axis AB. And then if you want the overall whole area, obviously I have to integrate, and when you integrate y squared dA, what you will be getting is moment of inertia of the area about AB. So the definition of moment of inertia itself is integration y squared dA, right? So this is about AB, but this is equal to, because of parallel axis theorem, if I know the moment of inertia about centroidal axis, which is represented by IZ here, right? So IZ plus the area multiplied by square of the distance between the two axes. The required axis is AB. The known axis, which is through the centroid, is XX, and distance between them is y bar. So y bar squared. So IZ plus y bar squared would be the moment of inertia of this figure about AB. IAB is equal to IG plus a y bar squared. Okay, this already we have done. Hydrostatic force on vertical plane surface, all this is done. Here there is a lamina, and then edgewise when we see it, it is like this, right? And all these notations and this expression we have already discussed. So highlighted part only, if you look at, F is equal to gamma AH bar. Gamma is the unit weight of the liquid in which the surface is immersed. Area is the total area of submergence of the area. H bar is depth of the centroid from the free surface. Please repeat it in mind. It is from the free surface up to the depth of up to the centroid. That depth is represented by H bar. So F is equal to gamma AH bar. If you want the depth of center of pressure, HCP, you have gone through all this. This is equal to H bar, that is H bar, plus there is some additional distance given by IG by AH bar in vertical surfaces, vertically immersed surfaces. Okay. Okay, this you can just have a look. Actually edgewise it is being seen, but when you open it up, it is actually a surface something like that. Here I have taken it as just one circular area, but actually speaking it is a random area. But to make you understand, we draw edge figure as well as how it looks when you look at exactly front of its face. That is also shown here. Okay, here there are a number of formulae, basics. You can just see here there is a rectangle, B the width, H the height, Y bar is the centroidal distance, area is given by B into H, Y bar is equal to H by 2, and centroidal moment of inertia. Moment of inertia for this axis will be B into H cube by 12. You should know all this because we will have to calculate IG, ICY if you want. Moment of inertia for this axis, obviously it will be H into B cube by 12. H into B cube by 12. Now if you have some magnitudes like 4 and 8, you can just go through all this. So this is some calculation. The units will be the unit raised to 4 would be the units. If we are using the distances in centimeter, it will be centimeter raised to 4. If it is meter, meter raised to 4, likewise. So for rectangle you should remember all these things. For triangle with a base B and an H as the height, the area is given by BH by 2. Position of centroid from the base, it will be Y bar, which is H by 3. Moment of inertia about centroidal axis parallel to the base axis. That's important. The axis is passing through the centroid, fine, but it is parallel to this base. Then it will be BH cube by 36. You cannot have a centroidal axis like that or like that, right? The axis passing through the centroid but parallel to the base. Then the moment of inertia about this axis, CX axis, will be BH cube by 36, right? Then ICY, because it is isosceles triangle, it will be directly given. Otherwise you have to break the triangle into 2 parts and then work out. This is not a ready-made formula for general triangle. I'll make you understand. Suppose there is a triangle something like that, which is not isosceles. The centroid will be approximately somewhere there. Say the height is H, the base is B. Then if I run centroidal axis CX, then this formula holds good. ICX, because the axis is parallel to the base, because of that BH cube by 36 is a general formula always applicable. But here the axis like that, if you take, this is not applicable, right? Only in isosceles triangles it may be applicable, but for general triangle it is not applicable. Now how to do that? You have to break this into 2 right angle triangles and work out for each one of them, and then find out the moment of inertia or centroid. Okay. Next, semicircle. For circle, the centroid would be the circle, center of the circle itself. You know that, center of circle itself. Okay. Now for semicircle, area will be pi r squared by 2, because area of full circle, you know that it is pi r squared. I'll try to write that for you. Or it is pi d raised to 4 by 4. And then y bar, that is distance of the centroid from again the base of the diametrical axis. This distance is given by 4r by 3 pi. Right. Now ICX, that is moment of inertia about this axis, they have given the expression, but easy expression would be 0. Write it neatly, 0.11 r raised to 4. That is the formula for moment of inertia of a semicircle about an axis passing through the centroid but parallel to the diameter, that is 0.11 r raised to 4. If you substitute pi value everywhere and then simplify all this part on this part, it gives you 0.11. Okay, now moment of inertia about vertical axis, it will be pi r raised to 4 by 8. It will be exactly half of full circle. Now in this case, the full circle, if we want moment of inertia about this axis, it will be equal to pi r raised to 4 divided by 4. So pi r raised to 4 by 4 is the moment of inertia of a circle with an axis passing through the centroid. Now this axis may be inclined, horizontal, vertical, it doesn't matter, because the axis will be always symmetrical. Because of that, it will be always pi r raised to 4 by 4. So whether it's a vertical axis, horizontal axis, it remains the same. But for a semicircle, if the axis is parallel to the base, then it will be 0.11 r raised to 4. And then if the axis is vertical, in that case it will be pi r raised to 4 by 8. Then for trapezium, you can have a look, but I would advise you to break this into triangle, a rectangle, another triangle, and then work out from basic fundamental principles rather than remembering all this formula. It would be always better to go by basic principles. Okay, centroid of an area is given by integration of x dA divided by integration dA. Moments of inertia about an axis, x-axis, y square dA, right, integrated over whole area. I have already shown this or used this information. Now when you change the axis, obviously the distances will be changing. Iy will be x square dA, and j represents polar moment of inertia, which is ix plus iy. Now if I try to show you, now the axis is this way and then another one is this way, and here you have got intersection, and let's say this is our x-axis, this is our y-axis. Obviously angle between them is 90 degrees. Moment of inertia about this axis, which is the axis falling in the plane of the lamina, is iy, and then about this axis ix. Now if you have an axis which is perpendicular to this, it will be sum of ix and iy, and because it is standing like a pole on a area, it's called moment of inertia, and that is z-axis, and moment of inertia about such an axis is known as polar moment of inertia, represented by the letter z about O. O is this particular point where x and y axis are passing through. Parallel axis theorem, you know already, we have been using moment of inertia about centroidal axis plus AD squared, that's what it is, and the radius of variation r is equal to root of I by a. It's a general thing. Okay, parallel axis theorem. Now you know that moment of inertia about, say, 1 1, right, 1 1 is required. Moment of inertia about 1 axis is required, and if you know by chance moment of inertia about centroidal axis, cx axis, which is given by bh cubed by 12, we can just see here, then we can write for I11 as sum of ICX, centroidal axis, plus this whole area A into the distance between the two axes, and distance between the two axes here, in this case it is A plus h by 2. So d squared, this d is equal to A plus h by 2. So d is nothing but distance between the two axes, distance from the centroidal axis to the required axis. That's how parallel axis theorem goes. A similar application over here, it is exactly the same slide, I believe. Okay, here there is a sheet which gives you a lot of information. You can just go through. Okay, here hydrostatic force on an inclined submerged surface. This is what is important. The edgewise look is something like this. When you open it up, when you look from the front, when you look from the front like that, how it looks is something like this. The area is A. The area is making some inclination with horizontal and angle theta, right? This plane is cutting the free surface at the point A, and then the point of intersection or the line of intersection of this plane and the horizontal is given by X or AX axis, right? So here elemental area dA is considered. This elemental area, which will be seen like that, has got a depth h from the free surface. I have indicated the centroid also, which is represented by the letter C, and that C is over here, and depth of centroid is HC, and overall maybe a resultant force which will be acting on this area will be represented by, let us say, F rather than Fr, and the point where that total force or total pressure force will be acting is known as CP, center of pressure. HCP would be the depth. HCP would be the depth of the point of application of whole force. Okay. Now again here DF, that is a differential force which will be acting on dA, will be equal to P into dA, because dA is the area, pressure intensity is P. P is given by gamma into H because H is the depth, gamma is the unit weight, because of that it will be gamma into H. P will be equal to gamma H. So if I substitute for dF, it will be gamma H into dA, but gamma is the unit weight of liquid. If I take it out, so integration of dA into H. So dA into H, it is nothing but moment of area, and that will be given by AH bar. That is total area multiplied by centroidal distance. That's why gamma into AH bar. Why this is so, we have already seen it in earlier slides. But anyway, what you should recognize or remember is that resultant force is given by gamma AH bar. Okay, now here from the geometry, H bar or HC, here it is written as H bar, is equal to YC. You can just see here YC. So in this triangle, if I try to draw the triangle, this triangle, I try to draw it here. This angle is represented as theta. This is, I'm talking it as a YC, and this we have represented it as H bar or HC. Now as this angle is theta, this angle is theta, because it is a right angle triangle, horizontal and vertical, we can write sine theta as H bar by YC. That H bar by YC is sine theta, that's why H bar is equal to YC sine theta. Similarly, the same argument goes for HCP, which is YP sine theta, and moment of inertia IA will be equal to IG plus AH bar squared. So this is geometry which we are going to use here often. Now again, by using Varignon's theorem, the resultant force and its distance represented by yp. I can make here resultant force F is acting, this distance is called as yp. So F into yp, that is moment of resultant force about point A, F into yp, is equal to sum of moment of all the small forces which are acting over the whole area. And in this case, that small force is taken as a df and multiplied by the distance y. So here we have y, df into y, integrated over the whole area. Now the force F is equal to gamma AH bar, already known. Yp is equal to integration df is given by gamma h into dA into y. Now h is replaced by y sine theta. So integration gamma y sine theta into dA into y. So this becomes gamma outside, integration y squared sine theta into dA. Or even sine theta is a constant because theta, the angle, is fixed angle. So gamma sine theta integration y squared dA. Integration y squared dA is moment of inertia about an axis like that, or an axis which is perpendicular to the surface of the paper or surface of your plane in which you are looking at. It will be popping out from the point A perpendicular to that axis, which is shown here as a line. So moment of inertia about an axis AX will be nothing but IA, right? Now this is gamma AH bar into yp, but if I replace again yp as hcp by sine theta, it will be like this. Now hcp will be equal to this sine theta, sine squared theta, ia, and this ah bar comes below. Now further simplification will give you sine squared theta into bracket ia bar ah bar, right? ia is what? ia is ig plus ah bar squared. We have seen this by parallel axis theorem, and divided by ah bar. Now if I take this inside ah bar, this will be h bar, right, plus ig sine squared theta by ah bar. That is what remains. Now overall expression for hc will be equal to h bar plus ig by ah bar. For theta equal to 90 degrees, this becomes sine theta, sine 90 becomes 1. Because of that, there will be simplification. Okay, hope you are able to see that. I'll read it for you. It is a rectangular plate 0.6 meters wide and 1.2 meters deep lies within a water body such that the plane is inclined at an angle 45 degrees to the horizontal, and the top edge is 0.7 meters below the water surface. Determine the total pressure force on one side of the plate and the location of the center of pressure. Fairly simple problem, but because it is the first time, you have to understand how to make out the meaning out of it. We'll see here. Now we'll try to draw the figure for this. So this is how the figure is. I'll explain this. See, the rectangle which will be looking like this, and this is not inclined at an angle of 45 degrees. This plane means actually, if I say this is the rectangle, you have to see it edgewise. So when you see it edgewise, this plane is making an angle of 45 degrees, not that this is making. So the plane is not like this. Only to understand how it looks, it is like this, but actually the plane is this way. So whatever dark line that is shown here, this is the actual case. The plane is making an angle of 45 degrees, but how it looks from front, that is shown here. Just to understand what this thickened line indicates, it is indicating 0.6 meter as the width, depth as 1.2, and this particular edge, the top edge, is around 0.7 meters from the free surface. The free surface indicated with a triangle on the top and few lines below. So this edge is 0.7. Because it is 1.2 this way, this is 0.6, and this is centroid, you know that. So this point is centroid, and we call this as h bar, right? Let me write that. This is h bar, and this point itself is g actual, right? This is the front view. Now, how to find out h bar? Obviously, it is 0.7 plus this additional distance we want. So, if I just show this vertical distance as y, so what happens is h bar will be equal to 0.7 plus y. Now, how do you calculate y? Because we know this as 0.6 and this angle as 45, because this angle is 45, right? If the angle is something different, accordingly we have to use. Now, what is the relation between opposite side and then hypotenuse from this triangle? Because it is a horizontal surface over here, here there is a vertical surface, and this is inclined. So I can write sine theta is equal to given by opposite side, that is y, divided by 0.6. So what happens is y becomes 0.6 sine theta. So 0.6 sine theta plus 0.7 will be giving you h bar, right? Okay. Here I have written h bar is given by 0.7 plus this extra distance, which is given by 0.6 sine 45, and it becomes 1.1243, and total pressure force will be given by gamma AH bar. Gamma is taken as 9790. You can as well take 9810, but in this particular example, it's a solid example where the value has been taken as 9790, but hardly it makes difference. 9810 Newton per meter cube would be the water unit weight. Area is given by 0.6 into 1.2. H bar, this is h bar, which is 0.7 plus 0.6 sine 45, which is 1.1243. This gives you the total force, 7.25 kilonewton. Okay. Now here HCP calculation means this point where the center of pressure. So this particular point, corresponding point over here, we'll call it as center of pressure, CP. Okay. Now the depth from here to, the depth from here to there, that is vertical distance from here to here, which will be represented as HCP. HCP is given by the formula h bar plus Ig sin squared theta divided by AH bar. Now Ig is given by BD cube by 12, because it's B into T cube by 12, because this way, right, the depth, it will be 0.0864. The area is 0.6 into 1.2. The angle theta in this case is 45 degrees. So you substitute everything. HCP will be this h bar, which is calculated over here, is 1.1243 plus whatever extra terminology Ig sin squared theta dot by Ah bar is there, it will be 0.0534. Obviously you can just see that it is negligibly small distance which will be getting added, and if the submerged surface goes more and more deeper inside the liquid, this contribution becomes less and less. Anyway, in this case HCP has become 1.777 meters. Okay, with this we'll stop here. Thank you.